Alright, everybody in their places. You guys ready on acid?
Ready on acid.
Ready in the blender?
Ready in the blender.
Tenfold. Go ahead and swap me the acid.
Let's get it Fracsim. Hotel wake up call got me getting up.
In this video, I'd like to talk about simulating current with the Fracsim meter. We'll go over both syncing and sourcing and the regular 2-wire and the 3-wire. The only leads you need for this are the gator leads, of course, on the right-hand side. You can see if you look at the back of the meter. If you actually look at the back of the meter, I'm going to be using this as a demonstration. It lines up where it says what's on this side lines up with that connector there. So I'll be using that for demonstration, but basically that connector, it shows you all the connections, the correct connections for syncing and sourcing current. Sourcing current is, of course, when you use 24 volts from the meter to drive the current, and syncing is when you use 24 volts from an external source. And I have a bench power supply we're going to be using for that. In terms of how you apply that to unit, if you were to consider a frac pumper and you wanted to simulate a pressure into the frac pumper and you wanted to use the power from the frac pumper system, the electric power from the frac pump system, you would use the syncing, not the sourcing. Now, in some applications you could source current into a frac pumper, but you would not be troubleshooting the whole circuit. Most of the time you would actually be syncing current. So anyways, we'll go over sourcing current first because it's the easiest. So like we talked about, if you look at this card here, the sourcing, it shows we're going to use current sim and follow that around to ground. And of course the red and the blue or the black indicates red would be hot or power supply positive from the unit, and the darker, the black or the blue would be the ground on the unit. So it depends, of course, on the pinout on the unit you're working on. So for us, basically, I'm just going to find the like we talked about, the current sim pin, and you can see it there matches up the shows current sim right there. Now, when you're looking at these leads, of course, they're double labeled for use on either side of the connector. So you see current sim is for use when you're on this side, and if you're on the other connector, of course, then it's going to be 485A, and that's how they're labeled here. So you can use this connector on either side. But for our application, current sim and ground. So current sim needs to go to the positive of what you're going to be sourcing into, and that happens to be the red lead on the 741 here, or equivalent. And the ground lead, of course, is the ground going on to the 741. And the meter here, you would just press number 1 for simulate and number 1 for current. And it automatically starts off at 4 milliamps, and you're going to see a couple things on here. You're going to see the set, which means set point, 4 milliamps. You're going to see the measured current, and this is actually what the meter is measuring internally. And you're going to see the loop voltage. This loop voltage is internal from the meter because we are sourcing. The output percent, that percent is based on a 4 to 20 milliamp scale. So, for example, 12 milliamps, I'll just do 12 right now, would show 50%. You can see over here, this is just the actual reading, showing you over there what it's actually doing. Some other stuff you got on the screen here. So on the bottom you see 1, 2, 3, and 4, and the corresponding current value beside it. Those are just, if you just want 4 or 16 real quick, you can just press that. Now the other thing you can do if you wanted a particular value, for example, 8's not on the screen. All you have to do is enter the value. So for example, 8. Just press 8. It auto places the decimal, so you can keep going if you wanted 8.5, or you can just hit enter, and it's going to change it to 8. So if you wanted 8.9 right there, just like that. And also you see over here where it says there's a box that says ramp, and you'll see 7 is a step and 8 is a sweep. So if you hit shift and then 7, you're going to see that it's going to jump. So you could either look there or there, but basically it's going 8, 12, 16, 20. It sits there for a couple seconds and it keeps going back and forth indefinitely. The other option, of course, shift again, you can hit F8, which is the sweep, which means it's going to gradually go through the 4 to 20 in just more of an analog instead of a step increments. And that's basically current sourcing. Now I'd like to go over sinking current. So basically when you're sinking current, you're taking power from the unit and you're basically using this meter as almost like a variable resistor and controlling the current back to the unit. So for us to do that, we need to use the bench power supply. Now if you look here and you look at sinking current, don't worry about this one that says 3-wire up here, we'll worry about that later. So where it says sinking current, you actually got 24 volts there on that, you're going to hook up 24 volts onto where it says 24 volts, that'd be from the unit. Again, red is from the unit, positive, and then the black is the return. So we're actually, instead of going to be going from a current sim to ground, we're going to be going from the unit into a 24 volts and then back out on current sim. So we're going to pretend 24 volts from the power supply is from the unit. So 24 volts from the power supply, which I have to turn up my power supply, I'm at 8 volts right now. So 24 volts is going to go into the Fracsim on the one labeled 24 volts. And current sim, is going to return to the fluke here, just so we can look at the value, and then the other side of the fluke is going to go to the power supply ground. And we're still in ramp mode, so you can see there. I'm going to turn the ramp off, or the sweep off, and go to 4 milliamps again. So you can see we're back at 4 and 4. Now this time, this loop voltage actually shows what's on the power supply. So if I turn my bench power supply down to 12 volts, it shows you that. And it's important when you're troubleshooting a current system. If you are working on a unit and there's a known loop supply, it's important that this is correct. If you, for example, know that the loop should be at 24 volts and you got 12 volts, there's a serious issue there. And the thing is, your simulator might work correctly, but the unit might not, because the electronics in this are powered by batteries. Pressure transmitters, they'll usually be stamped with a minimum voltage. So if you have an issue with your loop and you're only getting 8 volts, this is going to continue to simulate correctly. So if you see here we only have 7 volts, let's go even lower. We have 4 volts, 4.8 volts. Our set point is 4, but if you look, we're still able to simulate 4 milliamps correctly. Now the problem is it might work now, but it's not going to work when you put that transducer back in line. It's not going to work. That's why that loop voltage, monitoring it, is important. And also you'll see the measure, if we drop the loop voltage low enough, that I'm going to have to increase the target a little bit, you'll actually see the current, the actual measured current starts to drop off when your voltage is too low. You see this moves to open, and then the actual measured current is showing the measured current, and we do not right now have enough voltage. So you can use that for troubleshooting as well. But like I said, if you're working on a loop, the minimum you should see is 12, and most systems that I've seen built in the last decade are all set up for 24 volts, not 12 volts, which in that case you would see it way up here. And then all the options, same options apply. But what I want to do to demonstrate more with the loop voltage is I actually want to put a resistor in series. So I happen to have a 250 ohm resistor here, and I'm going to put that at the output of the Fracsim to demonstrate a load. So out of the current sim, when it goes into the fluke here, I'm just going to put this resistor in here. And so you can see what we're going to do is we'll go to 20 milliamps, and you'll see we have about 20 milliamps, we're about 21 volts. And let me just drop this down to, I'll drop this to 24, we'll do this again. So 24 volts at 4 milliamps. If I go to 20, we got 20 volts now. You see, that's because normally a 250 ohm resistor, 4 milliamp load, it's 1 volt drop. So really, we should have about 24 volts would be the total right now because of that first 1 volt drop. Now if we went to here, that 20 milliamps on 250 ohm resistor would be 5 volts. So we should have a 4 volt swing, which we do approximately. We're going about 4.3 volt change. But again, it's just an indication to show you more troubleshooting indicators that you could use to properly judge whether your loop is working correctly. If you, for example, if you knew the resistive load of what your PLC was, or whatever pressure recording device you have or analog readout you're using, if you knew the resistance of that, you can see the voltage drop when you go from the different values and get another assessment of whether everything's working correctly. And again, the same thing applies. It's just with the load in there, you'll see that as the voltage drops, it becomes more significant having the proper voltage when you have a higher load on the system. So now again, what I wanted to talk about, the last piece here, is the 3-wire current sim. Now the 3-wire current sim is pretty unique. I've never seen another meter with that function. And basically what it is if you have ever had to simulate current and you want to measure voltage at the same time. And the reason you want to do that is because you're having an issue and you're simulating and you just can't seem to figure it out, and you want to make a voltage measurement to see if there actually is proper voltage there. So what I've done with the meter is I've integrated some bits and pieces so that you can actually measure the voltage, all the voltages on the loop while you're simulating current. And you see that's why on here there's this 3-wire current sim. And basically it's the same as the sinking current, but you need that ground wire from the meter hooked up to ground on the unit. And it's a different menu. So I'm going to go back. I'm going to go to simulate. Now up in the top you're going to see 3-wire current. So I'm going to press that. 3-wire current sim. So you see the screen changes a bit, and our current is way out to lunch. It's not working right. And it's essential, if you're using 3-wire current sim, it will only work correctly if you have that ground wire from the Fracsim hooked up to ground of the unit. And of course, ground of the unit, in this case, is the ground of the power supply. Keep in mind, 3-wire current sim will not work on systems that go through optically isolated barriers or intrinsic barriers or stuff like that, because frame ground is no longer a ground, so it will not work correctly. So as soon as I hooked that up, you saw that went to 4 milliamps and everything kind of came in line here. So let's look what we got going on here. We got 4 milliamps is our set point. So we got 4 milliamps here. Our measured 4.1. Now that measured, because of the way everything's working internally in the meter, that measured is not quite as accurate, but it'll still give you an approximate value. On the transmitter, now this is a voltage measurement. This is the total voltage on the transducer, or what would be the transducer, what is now the Fracsim. So that'd be the actual voltage across the Fracsim. The supply voltage is 19.8, and that would be the actual voltage from the unit to frame ground. And this here, return voltage, this return voltage is the drop from the return of the meter to frame ground. So it's actually making 3 different voltage measurements. If I were to quickly draw that out so you can see. Basically what you got is, we'll do the instrumentation type drawings. Pressure transmitter. And you got a pressure recorder and our 24 volts. So the loop actually looks like this. You got 24 volts coming out of here, going into your pressure transmitter, or Fracsim, whatever, returning back to your pressure recorder, and then of course going back to frame ground. This of course here is just frame ground. Now, normally with 2-wire, the only measurement you could possibly make is the voltage measurement right there, and the current measurement right there. But by adding a third wire, and we'll call this now the Fracsim, by adding that frame ground on the Fracsim, you can actually make this measurement as well from here, from supply to ground, and you can take the voltage measurement from here to ground. And why that's useful, of course, is if you would have possibly a high resistance here or a high resistance here, you could actually see that with the voltage readings here, and then figure out which side of the loop is your issue, either the supply side or the return side. And I can demonstrate that here. So we had a 250 ohm resistor, if you remember. So right now we're simulating at 4 milliamps. Our supply voltage is approximately 20 volts, and we have a return voltage of 1 volt. So if you remember, 4 milliamps to a 250 ohm resistor is 1 volt drop. So everything looks good. So if you actually had a system that you knew the return resistance on, for example, most instrumentation systems, the older systems use a 250 ohm resistor. So then you'd be able to tell just by looking at this return voltage and the current whether everything was working okay. And I mean, if I go 20 milliamps, that should be 5 volts. See, it's 5.4, so it's a little bit out, but it's still within an acceptable level. I'm just going to put in there to demonstrate a possible failure, a 1k ohm resistor. Go back to 4 milliamps, of course. So it's a 1k ohm resistor, 4 milliamps, so we should have a drop of 4 volts, which we do. So we're starting at 20, or just under 20, and we should be at just under 16. And that is correct. And that is due to that 1000 ohm resistance. And if you actually see at the bottom here, it's actually giving us a warning now. It says return ohms high. And so this system, the 3-wire current sim measure, also includes these diagnostic messages at the bottom. So I can see some of the other diagnostic messages. I'm just going to turn down the loop supply. You'll see as soon as you drop below 12 volts supply voltage, it also says low supply. And if you keep dropping down right to nothing, it'll say no supply. So basically, it gives you every single measurement you could possibly need not that you could possibly need, but most likely ever need for troubleshooting a loop. So we have a resistance on the low side, and you can tell just because the supply voltage is still, I'm going to put my supply up to 24. So our supply is still 24 volts. So you can tell from, if we had this fault on a unit, a 1000 ohm load somewhere, you can tell it's in the return side by looking at these measurements. So we got 24 volt supply, so we know that the supply voltage is good, but our return is at 4 volts, and we're only pushing 4 milliamps. So if I were to try something like 16 milliamps, we're actually dropping 16 volts on the return, and we now only have 7 volts on the transmitter. And most transmitters will not operate correctly at 7 volts. So you can see from this information, you have return ohms high for one, but you can see it because the return voltage is very high. You can see that your transmitter now has only 8 volts on it. So you can tell right away that the problem is on the return side. So this system is useful for more advanced diagnosing of current loop issues. Now I'm going to take the 1000 ohm resistor, take it out, this back up, and instead of it being on the return side, I'm going to put it on the supply side, and we'll just see what it does. So now we're back. We've got a 24 volt supply. We have a little bit of a drop, voltage drop. It's just shorting it out right now, so theoretically there shouldn't be anything. There might be a little bit just from circuit protection inside of the Fracsim, so that's probably why we're seeing that 0.3 volt small drop there. But what I'm going to do now, like I said, I'm going to put this 1000 ohm resistor in this supply side, which is the 24 volts. If you were to look at this circuit, it'd be the 24 volts if I were to put a resistor in here somewhere. So I'm going to go ahead and do that. So you see now the supply voltage is dropped right down. So our supply voltage is now 11 volts. And the reason that's happening, you got a resistor in here, way too high, 1 k ohm. What's happening is you're getting a big voltage drop right here. So now these voltage readings here are obviously going to be low. So from this information, just like how we diagnosed the high resistance and return signal, you can see here that we have a high resistance in the supply signal, and the reason you're seeing that is because now our supply voltage, which should be at 24 volts, is now just by random chance the resistor value we're using has dropped it down to 12 volts, and you can see instead of the error message before being return ohms high, now it's low supply. So again, more useful information, and you can tell there's nothing in the return side. Our return voltage drop is pretty much nothing again. So you know that the problem's not on that return side, and the fact that our supply voltage should be 24. And you can kind of see if I were to put in a different value like 1 milliamp. Look at that voltage went up 2.5 volts, more than 2.5 volts, just by changing the current down to 1 milliamp. So you can tell that adding a little bit of current, you're having a huge voltage drop, so you can tell that there's definitely an issue, and the fact that there's no return voltage drop, you can tell that resistance is going to be right in the supply side.